Okay, so what I have now is I have a square wave multivibrator circuit built right here, and that inputs into this circuitry up here that runs the opponent lights, and that's what it's doing right here. You can see what happens is one light comes on the left hand side, and then that light goes down the left hand column, and then the right hand light comes on and then sends the signal down the column. And so that's the opponent circuitry. Now I also have it where I can adjust the speed of that by adjusting the potentiometer here. As I adjust this goes a lot faster now, back and forth. So you can see how it's blinking back and forth real quick. And then by adjusting the potentiometer here again, I can slow it down. And what I'll do is when I make the main circuitry for this, I can put bigger capacitors in here too to give it more of a time delay. And that's how that part works there. So now we have it checked out here for the opponent display working properly. And so now we're going to combine that with the manual inputs here and see how that works out there. And we're just going to give it a quick shakedown here of all of the display working. And that's coming up here now. So now we're going to check out the manual input here again. And we can see the green light going up the column on the left hand side. I'll put the right side on, the firing button, and it goes up on the right hand side. And so now the display works the way we want it to work. So we're just giving a quick dynamic check here just to make sure that everything is connected properly and everything's working properly. So now the next thing to do would be to start working on the object of the game. Now the object of the game would be that anytime a red light turns on down here, that would be an opponent score, on the left hand side or the right hand side. Anytime a green light comes on up here and the red light is on at the same time, that will be a score for the defense here, which would be the player against the opponent. Now what's going to also happen is the scoring will be up here and here for the opponent down here and for the player up here. But in order to be able to defend the missile base here by sending up the signals this way here, what's going to happen is whenever a green and a red light come on at the same place, that's going to cancel that, and that will stop the red light from proceeding further, and that would be intercepting the missile coming down. And so the idea is to keep on intercepting these missiles until you can get one up there to hit the top one up there and then score. Now in order to do all that, we have to start thinking about the logic circuitry that's going to be involved in producing that kind of results, and that's what we're going to start working on next. So what we'll do is we'll go to the drawing board now, and we will draw up some logic diagrams here. What I'm trying to do here is I'm trying to get a situation here that when a green light and a red light is on in one of the columns, a pair comes on, that it would go to an AND gate, and then the AND gate would give some sort of an output, and that's what we'll look at next. Okay, so what I'm doing is this is the transistors with the resistor capacitor coupling that makes the lights go from one stage to the next. That's what we'll call a ring counter. So what I have right now is I have the output going through a steering diode, it's a regular silicon diode here, and then to the output, which is the display, the LEDs. And the diode is here so as to isolate the output from other outputs so I can have a fan out. It's possible that I may have more outputs coming off of here, and without the diodes then I could have some interference. I could have currents flowing that should not be flowing in interacting with each other. So that's what these diodes are for isolation. So what I'm going to do now is I'm going to make some jumpers, and I'm going to make jumpers that will have a diode again, and then a jumper that goes out this way here that will be connected to the output of each one of these here transistor outputs here that run the LEDs, so that that can fan out of this, and it can actually input into the input of an AND gate then that will then have one red light and one green light. This will be the green light here, and this would be a red light here, and then we can have the AND gate go and do a specific function when it comes on. But right now I want to go ahead and put these here jumpers on here now. That's going to allow me to fan out from the outputs of these here transistors here now. Okay, these are the jumpers that I'm telling you about here. On one side here I have a diodes on this side here, and then on this side here I have very low resistors on here, about 4.3 ohms, and they're very, very low resistance. That's only so that I have a way to plug in these jumpers into the breadboard. That's all this is for right here. But here's the diodes, and the diodes are going to go to the transistor ring counters here. I got one set up here already. I'm going to go ahead and put the next ones in. So what I'm doing is I'm dropping down inside here and finding the outputs to the to each transistor and putting that in, and then I follow the other side here and I put it out here because this is where I'm going to be connecting to the AND gates from here. I'll be using this here to wire up to the AND gates. Right now, as you can see, my magnifying glass here, you can see through here. What I'm doing is I'm putting to all these outputs here now. Right here, I'm putting the diodes. I have the other side already on, fanned out. That's over here now. So these here run the LEDs, as well as now outputs are going to go to the AND gate. And so I'll finish putting this here bunch on, and then we'll start working on the AND gates themselves. I have all the jumpers all hooked up here now. And so now I want to make sure that all these here jumpers are hooked up properly, because remember, every one of these here jumpers here are connected to one of these lights over here. So what I'm going to do is I'm going to hook up the generator here and turn on one column at a time, and this will be the red lights. And I have an indicator light here I'm going to use. I'm just going to probe each one of these here outputs that we put in here, make sure that light lights up. If it lights up at every one of these, then I know then that that it's hooked up right. Okay, so I know that the left-hand column is hooked up right because the light's coming on, and I'll do the same for the other outputs here and verify that all the outputs are hooked up properly here. Moving right along here now, what I need to do now is I need to start working on the area here that whenever two lights come on, a green light and a red light comes on at the same time in the same spot, that they're going to cancel each other out. So what I'll need to do now is I'll make an AND gate, and I will hook up to one of these groups of LEDs here on one side, which would be the transistors over here. And what I'll do is I'll make it work that the red light will come down and put a green light up to it and see if they cancel each other. And if it does, then I know then that'll work. And what that does is that'll be an AND gate, and that will work each one of these here things here, the groups here. I have one little AND gate built right here, and what I have it is I have it on these two lights right here. When this red light comes on and this green light comes on at the same time, then it's going to feed into the AND gate here. And when it feeds into the AND gate, this here red light should come on. If that red light comes on, then I know then that this AND gate is compatible to the voltage output that is being developed at the circuit that's running this, which would be up here. It would be this circuit here and this one here. So what I'm going to do now is I'm going to input the buttons here to make the green light go up and see if it hits that red light, same spot here, and then we're going to check and see if that lights up over here. Yeah, I have it dark right now with the light off, so down here to the bottom of the screen will be a light will come on if these two lights here hit the same time. So let's give this a try now. Okay, do you see that light in the bottom of the screen come on? Okay, that light down here, the light down here came on, and so that means then that the AND gate is working. Let's do it in the light here now. Okay, we got to see if I don't know if it showed up in camera or not. Let's see here. Okay, so we'll just see if how that lights up. Okay, so we're down there was what I'm looking at. So that was just monitoring to make sure that this here was actually work at the same time, coming together as an AND gate input to that. Okay, so let's go ahead and start thinking about now how we're going to cause these two lights when they come on to cancel each other, because that's what we need to do next. We're going to do now is whenever this here red light and green light comes on, we're just going to use a different example right now, that it's going to cancel the signal from going up on the green lights and coming down the red lights. Are going to cancel each other out. And so we need to go to the schematic now and start thinking about how we're going to design a circuit to make that happen. That's coming up next. I have a little bit of this here drawn up on my CAD program here to do some design work here now. What we have here right now is this would be the column of LEDs. We'll say this is the red LEDs going across. That would be the left-hand column going down of red LEDs. And what we're going to do is we're going to think of a way of how we can cancel a signal. Let's explain here a little bit of how the signal goes from one LED to the next in the line. This would be maybe a line of 5 or 6 like we have over there on the display. And let's see what we have here. Okay. Whenever everything is in stable condition, there's no signal being applied to the first transistor. The transistor will be turned on, and every transistor will be turned on, and every transistor would be in pretty much saturation. When they're in saturation, then they're going to be bypassing the current through from the LED line here, and all the display LEDs will be turned off because they'll be shunting the voltage across there, because the voltage across the collector emitter will be much less than the voltage across the LED, and therefore the LEDs will be off. Now what happens is when a signal comes in, it has to be a negative going signal that would come in. It would then turn the base of the first transistor where the signal comes in at to ground, and it would cause the transistor to go into cutoff, and when it goes into cutoff, then its collector voltage will rise. When the collector voltage rises, it'll begin to charge the capacitor in front of it up, and it will charge it up to the base emitter junction of the second transistor. Now that would cause the second transistor to come on harder yet, so it would keep its output off like it's supposed to. But as this capacitor is charging up through here, it gets to a certain value where it's fully charged, and then when this transistor comes back on again, the negative signal will be released, and then the transistor comes back on again. As it goes back on, the positive flow through the base emitter junction here causes current to flow through here again. The transistor goes back into saturation, and it begins to knock down the voltage at the capacitor, and it takes it below ground, because right now it's about 4.3 volts or so dropped across here. And what happens is, because this is around 0.7 volts here, this will be about 5 volts sitting here, and about 4.3 volts dropped across here. It's positive here. When this transistor goes into saturation again, it's going to drop just about 0.3 volts. And then we're going to have a negative value here, and that's what happens is that negative value causes this capacitor to discharge because it goes below ground on this side, and causes to go into a very strong negative value, about 4 volts or so negative, into the base of this transistor here, which causes this transistor to go into cutoff, which then causes this capacitor to charge up, and it just keeps on going right down the line like that there. That's how it sends the signal down through there and becomes that ring counter that we have set up there for the displays. Now with all that discussion in mind, what we need to do now is, instead of the signal going from one capacitor to the next, we need to be able to cancel that signal at that particular stage right there. So when this LED here comes on and the LED of the other column comes on at the same time, that AND gate that we built over there, we want to show how that AND gate is going to now be connected in such a way that it's going to stop the signals from this capacitor in this particular incident here from being transferred over. So in order to do that, we have to be able to take the output of that AND gate into something place here to do that. And the only thing I can think of is that if we were to discharge this capacitor, we have to discharge a capacitor. We can't do anything other than discharge a capacitor, so that's the only way the signal can be stopped from advancing. So one way to do that would be to probably use an NPN transistor, let's say. Let's go with an NPN transistor here. And let's put an NPN transistor right here, connect it to here, and connect this to the positive side of the battery. And then let's put a resistor in here. And I like to work with like 2Ks and 10K ohm resistors, so I'll just put a 2K in there for right now. And if we put a 2K ohm resistor in there for an input to the AND gate, here's what I think might happen. Is what we do is, when the AND gate comes on, as we were showing over there, when 2 lights come on, it turns the AND gate on. That AND gate would then have an output that would turn this transistor here on. And when that comes on, that should then cause the voltage across here, because remember now we're at 5 volts here and 0.7 volts here. So we have a we have this capacitor charged up here, so that whenever that AND gate comes on and turns this on, this should then cause this to go a high positive discharge in the capacitor, so that signal can no longer be directed into the base of this, because it will shunt the base of this through this transistor here. And that's what we're going to do next. We're going to hook up a transistor here and see how that does and work in that. The setup I have over there now, this here is the column of red LEDs, and is the column green LEDs. The output of the one LED, red LED, would go into the input of one AND gate here. And then at the same spot there, the green LED would put it input into the same AND gate. The output of the AND gate will go through a steering diode. One of these goes to the transistor up here to discharge this capacitor to keep the signal from transferring further. And the same thing down here. It goes down to this transistor that blocks the signal from this capacitor to continue on. And so what we're going to do now is see if this actually works, see if this will actually cancel out the lights now when they come together at this AND gate. Jumper wires I made here. It has two diodes on one end and has two 2K ohm resistors, one on each end here, that will go into each input. And that's what I have here. I have the cable set up here, and here's the AND gate. And I'm going to remove that LED that we're using for to check that. We're going to remove that LED, and we're going to put the diodes now in that at the output of the AND gate. And so now we have the diodes in place of the LED. The LED was there to monitor the AND gate to make sure it comes on, but we have to remove the LED because we have to make sure that we're getting a heavy enough voltage output. The LED would only knock it down about 1.8 volts. So now we have the diodes in the output of the AND gate, just like our schematic showed. And so now we're going to go ahead and check and see if these two lights cancel each other out when they come together. That's coming up next. Okay, let's go ahead and do this now. Okay, both the LEDs came on at the same time. They both came on at the same time, but they're not canceling each other out. We know that the AND gate is working properly, so what we've got to do now is take some voltage measurements and find out why it's not canceling each other out. I have my analog voltmeter hooked up here to the output of the AND gate. And first of all, I want to find out what output voltage my AND gate is giving. And then I want to check and I want to see what voltage it's going to take to make that work. Those lights cancel out. So first of all, I'm going to input a green signal. Okay, we went to about, I had to set on 2.5 on the scale. Without any input at all, when that red light comes through there with no green light, it goes up to about not quite a half a volt. When the green light comes on together, and it goes up to about 1.1, 1.2 volts only. So we're only getting about, there's 0.5. No, that's less than that. That's about 0.6 volts only. So what we're getting roughly around 0.6 to 0.7 volts on the output of the AND gate. And that's when both the red light and the green light come on. When one light comes on only, it moves to about 0.4 volts. And so we're only getting about maybe 300 millivolts right there. Now right there when I have the steady green on and the red comes in, it moves to about 0.75 volts, almost 0.8 around there. So we're less than 1 volt output on the AND gate. So now I want to find out what for voltage I'm going to be able to need in order for this to work properly up here to cancel each other out. And that's what's coming up next. Next thing to do now would be to remove these here diodes that we're using to run the outputs there. Those diodes are used to turn these LEDs off. And we're going to put a resistor substitution box here, and we're going to check the voltage here and see what voltage it takes in order for that to work. I'm going to hook my voltmeter up to the LEDs, or to the diodes here. Okay, now I have my substitution box set up here, and I have it going to those there diodes there that running the LEDs here. What I want now, right now, the LED is going across. Now, when this here LED stops here at that point there, then I'll know the voltage it's going to take to do that. So I'm going to my substitution box here, and I'm at 1 megohm, so I'm going to start reducing now the resistance on this, and I'm going to be checking the voltage here whenever that light starts to stop at this point here. Right now it's still moving, so I'm going to decrease it further. Now we're getting a little bit erratic. It's getting a little erratic now, but let's keep on going here. I'm at 51K now. Now it's stopping. Let me go to 61K. Stopping. 71K. Okay, good. So at around 71K, so if I go back to 61,000 ohms, 61K, it stops. It's working properly. If we look at the voltage, I'm on a 10 volt scale now, so I'm 10, 8, 6, 4, I'm about 2 volts. So it looks like about 2 volts output from the AND gate would actually cause that to work properly. Let's try the green light now. See if the green light stops. There's the green light. Yep, the green light is stopping also. So now we have the red light and green light stopping. We're supposed to, and that would be with a voltage of about 2 volts to make that happen. If we lower the voltage now by increasing the resistance here, we're down to about 1 volt now, and again the LEDs start going through again. There's no more output from that there voltage box. So we know now that 2 volts is what we need, at least 2 volts off of the AND gate to make that stop and cancel each other out. So that's what we're going to work on next. Here's where we're at with this now. We have this here set up here. And what I've been doing is I've been working on trying to raise the voltage across the LEDs. We're putting more diodes in there to try to get more higher input voltage to the AND gate. But then it's starting to run a little erratic that way, and I want to keep everything working properly like it is now. So I decided to abandon the input side of the AND gate, keep everything the same on the AND gate, keep everything the same on the inputs of the AND gate, and do all the work on the output here of the AND gate. So what I'm going to do is I'm going to look for a way that I can increase the voltage output of the AND gate. We need to get this up to at least 2 volts on the output. That's the minimum. So the only way to do that would be to work it in such a way where I can get some sort of a circuitry in there that could amplify the signal. Also with the AND gate here, we realize is that anytime we get a small input in here, we do get a small output out through here yet. It's negligible, but it is not fully saturated, so therefore we're going to be getting some sort of a amplified signal as this here inputs come in, and we want to try to keep the output signal when it goes into here more steady and more steady, and then have it trigger. I don't want to use a Schmidt trigger circuit, but a Schmidt trigger circuit type function would work for this here. We need something that's going to snap fast into a high output voltage and remain low until we get a valid signals in here on the inputs. So instead of using a Schmidt trigger, I'm just going to come up with some sort of a buffer circuit, a digital buffer circuit, and we're going to see how that works. Amplifier that I came up with here. What it is it's 2 inverters here, but the output of the second inverter here, they combine together to form a buffer amplifier. But the output of the second inverter here, which becomes the output of this buffer amplifier, has a good output impedance here. We have a very low 330 ohm resistance here that's connected to the positive side of the battery. So what we have here is a good current output here that can drive and fan out to a lot of other inputs. And I think it's going to work good here because of the fact that we're not relying anymore on a voltage drop across this transistor here on the AND gate to give us our output, but rather we've got a clean output coming directly from the collector resistor here, which gives us more of a stronger output as well. We can get this thing up to almost 4 volts if we needed to on the output. Now by using this transistor here on the input side right here, we can have a good input impedance here too. I'm using a 10 k ohm resistor here, and so these 2 transistors combined together can give me a good amplification that the change in the output of the AND gate here can give me a good change here, but at the same time make it snap up fast, but also keep it from changing until both inputs come in on the AND gate. I have a 2 k ohm resistor here to ground on the output here, so as to keep any kind of signals from getting through here until a valid input signal comes in. So that keeps that kind of like at a ground potential until while this transistor here is in saturation as well. In other words, if any small signal comes through here, this could change this a little bit and cause a signal output. We don't want that. We want to keep that working grounded here until this transistor gets a valid signal to go into cutoff. And that's when this transistor comes on, when the AND gate comes on, when both inputs come in. So let's go ahead and build this and see if this takes care of it. Okay, I got the buffer amplifier built in here and connected in here. So what I'm going to do now is turn everything on, and I want to see how that works now. I'm going to input a signal here. Let's get the speed up a little bit. Okay, here we go. Input a signal. Okay, it looks like the it's working, but what's happening is it looks like it's working pretty good, but what looks like what's happening is sometimes the green light gets canceled and the red light goes through. So one light cancels, but it seems like the red light wants to dominate more here over the green light. So whenever I get the input in, the red light swallows the green light. It cancels the green light, but the red light continues on. But they do get an input into there, so it is working to that point there. So now you got to find out why that red light's not canceling with the green light. The red lights are using 100 microfarad capacitors to relay the signal, and the green lights are using 33 UF capacitors to relay the signal, so that the green light goes faster than the red lights. And it seems like the red lights are not discharging long enough, and that's why the red lights continue going on while the green lights are canceling. So what I need to do is I need to make a delay on here so that it gives enough time to give a good discharge on the red lights as well. Okay, in order to give a delay, it looks like the best thing to do would be to put a capacitor across the output of the transistor here on the AND gate itself. In other words, if we put a capacitor across the collector emitter of the transistor here, that means then that whenever this goes positive here, it will discharge the capacitor. But then when the AND gate goes off, then the capacitor will start charging up through the 2 k ohm resistor, and that charge up will keep a delay of positive voltage on the base of this until the capacitor gains a charge. Let's see what that looks like here. If I connect, let's say, a 100 UF capacitor, and connect that to the positive side of the battery, connect this to the emitter. That means every time the AND gate comes on, it discharges the capacitor. When the AND gate goes off, the capacitor charges up through here and gives that delay that we need to keep this circuit running over here long enough so that this here can discharge these here capacitors up here that are larger that they need to be in order for that to work properly. Let's see how that works. Okay, so I put a 100 UF capacitor across the collector emitter of the AND gate transistor. That means every time the AND gate comes on now, that it will discharge the capacitor, and then when the AND gate switches off, the capacitor will charge up and keeping a positive voltage on the buffer amplifier, which would then keep enough time constant longer before the output goes back to low again. So let's go ahead and see how this works now. Alright, here we go. I'll speed this up a little so you can, alright, here we go now. There it is, it's working. The green and the red light are shutting themselves off at the same time. There it is, it's working. Here we go, ready? Boom, it's working. There it is, it's working. Okay, it's working. So that's all it took. It took a capacitor in there to delay the off time of the output of the transistor. So now we have that working properly there. The red light and the green light cancel each other out. So all I got to do now is build the same circuit now 4 times for each column here. There's a total of 8 of them, and then we'll have all that part done to that point there.